Hello, and welcome to our deep dive into chemical kinetics. In chemistry, we often ask if a reaction can happen. But today, we're asking a way more interesting question. How fast does it actually go? So, let's get started. You ever wonder about that? Why does something like a piece of iron rusting take, well, seemingly forever, but an explosion is over in a literal flash? That incredible difference in speed, that is the entire heart of chemical kinetics. It all boils down to something called the rate of reaction. So here's what we're going to cover. First, we'll get a solid grip on what kinetics actually is. Then we'll figure out how you measure a reaction's speed. After that, we'll look at all the things that can control that speed. We'll even learn how to write its official rulebook, which is called the rate law. And finally, we'll clear up some common confusion between two key terms, order and molecularity. All right, first things first. In this section, we're going to define exactly what we mean by kinetics, and just as importantly, what we don't mean. Okay, get ready for a mind bender. Thermodynamics, it tells us that a diamond will eventually turn into graphite. So why don't our diamond rings just crumble into pencil dust? The answer, my friends, is kinetics. You see, thermodynamics tells you a reaction can happen, but kinetics tells you that it might take millions and millions of years. And that's the huge difference. Feasibility versus actual speed. So if kinetics is all about speed, how do we, actually put a number on it? How do we measure the rate of a reaction? Well, it's a pretty intuitive idea, actually. We just measure how much the amount of a substance, its concentration, changes over a certain amount of time. Are the starting materials, the reactants, disappearing really quickly? Are the things we're making, the products, showing up slowly? That's what we're measuring, the change in concentration over time. Take a look at this graph. See that curve? It shows the concentration of our reactant, and it's going down as time goes on, which makes sense. Now, if we want to know the average speed between 2 points in time, say T1 and T2, we can calculate the average rate. But what if we want to know the speed at one single precise moment? For that, we need the instantaneous rate. And that's just the steepness or the slope of a line that just barely touches the curve at that one point. Now, don't let the math here scare you. I promise this is just a fancy way of writing what we just saw on the graph. That little d just means a tiny instantaneous change in. So all this equation is saying is that the rate is the instantaneous change in concentration over an instantaneous moment of time. It's the perfect mathematical way to describe that slope we just talked about. So what's with the plus or minus sign? Well, think about it. The concentration of reactants goes down, so its change is a negative number. But we like to talk about speed as a positive thing, right? So we just stick a negative sign in front of the reactant's rate, and that makes the whole thing positive. For products, their concentration is going up, so the change is already positive. We don't have to do a thing. Simple as that. And what are the units? Well, if the rate is just concentration divided by time, the units are pretty logical. Concentration is in moles per liter, time is in seconds, so the unit for the rate is moles per liter per second. Okay, so if we can measure a reaction's rate, that leads to a great question. Can we control it? And the answer is absolutely yes. In this section, we're going to look at all the different control knobs we can turn to speed up or slow down a reaction. Let's start with 3 of the big ones. First up, concentration. The more molecules you cram into a space, the more likely they are to bump into each other and react. Make sense? Second, temperature. When you heat things up, the molecules zip around faster, which means more collisions and more powerful collisions. And finally, the nature of the reactants themselves. Some chemicals are just, naturally more reactive than others. And here are a few more. A catalyst. That's like a chemical matchmaker. It provides an easier path for the reaction to happen, speeding it up without getting used up itself. For reactions with solids, increasing the surface area, like grinding a chunk into a powder, gives the reaction way more places to happen at once. And for gases, cranking up the pressure squeezes the molecules closer together, which basically just increases their concentration and, you guessed it, the reaction rate. Okay, we've established that concentration is a huge factor. So, how can we describe the exact mathematical link between how much stuff we start with and how fast the reaction goes? Well, that's where something called the rate law comes into play. The rate law is basically the rule book for a specific reaction. It's an equation that tells you precisely how changing the concentration of each ingredient is going to affect the overall speed. And this is what it usually looks like. The rate equals K, that's a special number called the rate constant, times the concentration of reactant A raised to some power m, multiplied by the concentration of reactant B raised to some power n.
Let's break that down piece by piece. K is the rate constant. It's a unique value for every reaction at a specific temperature. The square brackets A and B are just chemistry shorthand for the molar concentration of A and the molar concentration of B. And those little exponents, M and N, those are called the orders of the reaction. They tell us just how sensitive the reaction speed is to a change in each reactant's concentration.
Now, this is the most important thing to remember about the rate law. You cannot, and I'll say that again, you cannot figure out what M and N are just by looking at the balanced chemical equation on the page. You have to go into the lab, run experiments, and actually measure how the rate changes when you change the concentrations. It's an experimental thing, not a theoretical one. So that brings us to our last big idea, and this one is super important, especially for exams. We have to be really clear on the difference between the order we just talked about in the rate law and a totally different concept called molecularity. They might sound a bit alike, but trust me, they are not the same thing. This table breaks it all down perfectly. Just look at the determination row. Order is found through experiments. Molecularity is theoretical. You figure it out just by looking at a single reaction step. Now look at values. The reaction order can be 0, a whole number, or even a fraction. But molecularity, because it's literally just counting how many molecules are colliding, it has to be a small, positive whole number, usually 1, 2, or 3. That's a huge difference right there. Phew. All right, let's do a quick recap. Kinetics is all about speed. We measure that speed, the rate, by seeing how concentration changes over time. We can play with that rate using control knobs, like temperature and concentration. The exact formula that connects rate and concentration is the rate law. And, say it with me, it has to be found experimentally. And finally, the order of a reaction comes from that experimental rate law, and it is not the same thing as the theoretical idea of molecularity. And here it is, all the key stuff on one slide. Think of this as your personal flashcard for the exam. The rate of reaction is the change in concentration over time. The units are moles per liter per second. The rate law is rate equals K times A to the M times B to the N. And the overall order is just what you get when you add up those exponents, M plus N. Lock these ideas in. And that brings us to one last question to think about. We've built a really strong foundation here. We know what controls the speed of a reaction, but we haven't really answered the deeper question, how? I mean, on a molecular level, what is actually happening when we turn up the heat or add a catalyst that makes everything go faster? And that is the perfect place to stop for now, because that's exactly what we'll be diving into in part 2 of our look at chemical kinetics. We'll explore something called collision theory and the super important idea of activation energy. I'll see you there.